All right. So let's talk about the Kalman filter, the celebrated filter in a modern control system theory. This is Professor Kalman uh, who proposed this filter. Even though it's a filter, we call it a filter, right? It's a very broad name. Uh, it's an estimator, basically. Okay. Uh, this filter can estimate your state variables. Now remember when you dealt with the state feedback control, right? If you want to implement state feedback, right, state should be available to you in the first place. If the states are not available, you cannot implement state feedback control. Okay. So if the states are not available, we design an observer, right? We design an observer to generate the states. That's what we do, right? Now, so that is if you don't have states, right, available to you. But if you have states available to you, still you have a little problem. Okay, whether these states are correct, accurate. Okay, because you use sensors uh, to measure state variables. Say you are driving a vehicle, you want to get your position, right, using maybe GPS, right? Or turning the wheel, right? In one wheel, one turn, how much it goes. And then if it turns 10 times, how far away you are from where you were, right? So these are sensor systems to predict your position. Okay. Now, there are errors in these systems, GPS errors, wheel encoder errors, all these things, right? Sometimes the wheel turns, but it doesn't move. The vehicle doesn't, right? When you are in muddy terrain, this happen quite often, right? You're trying to move out of this area, but you are stuck and the wheel turns. So if the computer which runs this state estimation doesn't know that you are not moving, it will keep counting the wheel turns, right? But without knowing it, it's being slipping, right? So therefore, these errors are there. Even though you have the sensor to measure the state variables, right? We don't believe it 100% because there's always an error. That's why when the sensor manufacturers have this data sheet of all of these sensors and tells you what is the error and variance, right, of that particular sensor. So how do we deal with the sensor feedback if we don't rely 100% on the values, right, that the sensor gives you? So far, we didn't have this problem, right? We assume sensor feedback is perfect, acceptable at least, and then we use it without asking any questions, and we implemented the control loop, right? So if the sensors are reasonably good, you will have a better system, right? Running to your expectation. If the sensors are crappy and there are errors in the sensors, we are on this discussion today, how to deal with that kind of not very accurate sensors. Okay. So let's start talking about the basic features about Kalman filter. So Kalman filter is an algorithm. It's an algorithm. Okay. So that's why I said don't look at the Kalman filter as a standard filter, low pass, high pass, and all that, right? This is not that kind of filter. It's an algorithm that uses a series of data observed over time, right? It takes the data from the sensor, right? So sensor has some noise, as I said earlier, but it has the state information as well. So it's it has the information, it communicates to you about the state variable, right? Even though it has a little bit of noise on top of that, which contains noise, as I said, and other inaccuracies to estimate the unknown variable accurate. So when I say unknown variable, I refer to the state variable that is being measured. Okay, the genuine, the true state variable is unknowable. There's no way to find that out because the only way to find that out is using a sensor. All of the state variables are like that. You use a sensor, okay, or a observer to read that. And in that process, what you have is the reading, not the actual uh, state. Okay, so right. Uh, that's why we cannot get rid of this noise, right? No matter how hard we try, there's select lines. Using Kalman filter, you can get an estimate. The filter, Kalman filter will estimate a value which is very close to the true state, okay, even though there is noise. So that is why this filter is very, very famous in signal processing and state estimation. It was proposed by Rudolf Kalman in 60s and became a standard approach for optimal estimation. This filter is real time. That is the other thing about the filter. It's real time. You can implement it in real time. Okay, it's kind of fast, right? It doesn't deal with historical data, right? To estimate the value. It's recursive. It works then and there, right? And efficient estimation algorithm. And it comes in various forms. Standard Kalman filter, which we are discussing here, standard Kalman filter, and extended Kalman filter, which is for nonlinear systems, right? The standard Kalman filter is for state space models. Remember, x dot equals ax plus bu. That is the linear, right? Based on that, we're going to develop the filter. If you don't have that kind of model, if the system is set of equations, but you can't put them into x dot equals ax plus bu, system is nonlinear. And for that, we have to use the same set of equations of the plant and develop the Kalman filter using that nonlinear plant. Then we call it extended Kalman filter. And there's another one called uncentered Kalman filter, UKF forms, right? So different forms of Kalman filter. Right. Now, there are some prerequisites before you can understand how the filter works, Kalman filter works. We need to understand some statistical terms here, right? Because it's a statistical filter eventually. It works with the probabilities, variance, means, etc. You remember all these things in statistical probability and statistics modules earlier, right? What is mean, what is variance, etc. So you need to refresh yourself on that if you want to understand Kalman filter and how it works. So Kalman filter has these features. It has minimum variance. So what is that? When I say minimum variance filter or estimator, it means that when the Kalman filter says something, let's say position, your position is 10 meters now with respect to 0, right? 10 meters. It's not exactly 10, right? It's a probability distribution. It's more likely to be around 10. Could be 9.5 to 10.5 in that area. Okay. So that is kind of variance. How much you estimate uh, and the actual value, right, differs from each other by how much. If it is a really good sensor or estimator, the variance is very small. right? But if you have a very low cost, cheap sensor, or your filter is not very good, right? It will have a higher variance. So when I say 10 meters, it could be anywhere between 8 and 12. That is a wide variance, 8 and 12, right? In the middle is 10, of course. Whereas in the previous case, it's 10, but it could be 9.8 to 10.2, right? Very narrow variance. So when we say this is an expensive sensor, this is what we refer to actually. Variance is small. When it predicts, gives you a value, right? It would be very close to the actual value with a very little variance. Second thing, zero mean error. Zero mean error, which means you have the actual state, you have the filter estimate, right? There's an error between the two, right? And earlier we said variance, it flips back and forth, right? This moment it could be, actual value would be 9.8. Next moment it could be 9.7. Then next moment it could be 10.1, like that. I mean, the filter estimate, right? Whereas the actual value is 10. Let's say your vehicle, you drive 10 meters and stop. It's 10. The Kalman filter says 9.9, 10.1, 9.75, 9.82, 10.15. Like that is a probability kind of thing. It predicts something around that, like in a random fashion. Okay. But it doesn't go to 6, 7 in the lower side or 13, 14 in the other side, right? It's a probability process. There are numbers coming in, right? But they are all concentrated around 10. So variance is very small. So small, narrow margin and estimate varies. And if you calculate all these estimated values and add them together, divide by number of estimates, right? Your answer is zero, which means on the average, there is zero, zero mean error. So these are the properties of Kalman filter. Third one is recursive, which means you can run it again and again and again, right? Recursive filter. Now, it's time to show you the filter, right? How it works. Now, here you can see um, a plant over here, right? This is the most important diagram for this discussion. This is our plant, and we give a control signal to the plant, and we get the output from the plant, Y. And Y is the state, okay? It comes from x1, x2, x3, and so on state variables. And this is this is probably one of these state variables, right? Preferably the first one in most cases. Now, how we fit the Kalman filter into the plant is like this. So this is a Kalman filter. We don't know what's inside as yet, right? But similar to the observer, remember? So Kalman filter is kind of observer in a way, right? So it's working in parallel with the plant. So Kalman filter has this information about the plant, okay? Like the system matrix A is known. Kalman knows it, okay? So part of the plant is over here. This is somewhat similar to the observer design, right? Parallel arrangement. So the control signal goes to Kalman filter as well, okay? In addition to that, you have a sensor to measure, say, this Y, right? State. This is the sensor, and this is sensor reading. So sensor tells you something. Yes, the reading of the sensor. It goes to the Kalman filter as well, right? So we give this letter Z for the sensor output, sensor reading. So Kalman filter knows three things. Number one, it knows the plant model, system matrix A, and also BU, AX plus BU. A and B are known by the Kalman filter. And it knows what is the control signal right now. And also it knows what is the sense, does the sensor says. Now you can figure this out, what's happening inside the Kalman filter. Okay. On one side, it has the control signal as well as the plant model so that it can calculate the next step, right? If you look at the state transition we did earlier, Kalman filter can run the state transition, okay, and find out what is the next position entirely using the state transition. That is one approach. Second approach, the sensor reading. Sensor tells where you are right now. So now you have two things together. One is the plant prediction using plant model and the control signal. The other one is you using your sensor. Okay. Remember the example I explained at the beginning of the class. You are driving a vehicle, right? You want to find out where you are, right? From where you were about a few seconds ago, right? Few seconds ago, you were at 0. And where are you now? If I ask you this question, simple answer is okay. Measure the circumference of the tire and calculate how many turns up to now, and you can calculate the distance. So it is how the plant works. What I explained is x dot equals ax, that model. You use the plant dynamics to calculate your next position if you know the input. Okay. So, or in the car model, again, example rather, you use the GPS, which tells you your position, and that is this set. So filter has to combine or fuse these two together and produce your position, which is state estimate, and we give it a name x hat. This hat indicates that it is an state. Okay. So here you have the true state x. This is the estimated state x hat. So once you estimate it, it goes back to the filter as a feedback. This is how you bring Kalman filter into a control system, right? And put it in parallel with the plant. So every loop back, right? Kalman filter predicts a value, estimate, right? And plant has the actual state, which is not known to anybody. And we want to make sure, the Kalman filter will make sure that the state estimate is very, very close to the actual plant state. Okay. It is better or more accurate than the sensor reading. All right. If the sensor is very accurate, perfect, there's no need of using Kalman field. Use the sensor and read it. You know where you are, right? But thing is, the sensor has its own noise. That's the problem. So if we combine plant dynamics and what it says as through the state transition, what is my present value, and the sensor tells your present value, you have to combine these two together. And that's happening inside the Kalman field. So that's how the Kalman filter is arranged or placed in a control system. Now I want to take your attention to two things um, in this system. One is plant noise. Look at that one. For the first time you are hearing this one, plant noise. We have never talked about plant noise, but in fact, this is unmodeled dynamics. When you write down the basic equations of a plant, right, there are certain things that you do not model, right? Perfect model of the plant, any plant, is not known. It's not known. Your mathematical modeling takes maybe 80% of the plant or 85% of the plant. Other dynamics are simply not known. But when you deal with the plant, if you look at the state that is coming out, right, as a result of the control signal, has all of these dynamics, not only what you model mathematically, but other unmodeled dynamics as well. They contribute to the state. But unfortunately, in our model, x dot equals ax, we don't have all of these dynamics. Therefore, if you go through the model and predict your position, it will be different from your actual position, because actual position is contributed by all of the dynamics in the plant, modeled and non-modeled. So therefore, it is not very good to use this wheel kind of thing. Remember, measuring wheel and all that, and find your position, next position using just the plant model. It's not very accurate. That is the first thing I want to tell. The other thing is sensor noise. You can see it over here, sensor noise. All of the sensors, they have noise. So therefore, when the sensor tells you 10 meters, we can't take it for granted, right? So how much of this is an error, right? Will it be 10.2 or 9.8, whatever? That noise is there. So neither of these two methods is perfect and accurate enough. Okay. Prediction by the plant model and sensor reading. So that's why we need somebody to consider all these things and then come up with some more accurate estimate. So going forward, we do some assumptions. What is that? X hat state estimate is very close to Y. Y is the actual one. This is what we want to achieve, right? What we want to achieve. Eventually, Kalman filter output should be very, very close to the actual output. I'll show you some results later, which shows that Kalman filter is actually predict the true value, right? Very, very closely. We therefore say the expected value, because X hat Y, these are all probabilities, right? You continuously your position changes and continuously your estimate changes. These are not just numbers, right? They are changing all the time, like in a probability. So if I want to say X hat and Y are equal, it's more meaningful if I say the expected value of X hat minus Y is equal, right? At any moment, there can be a difference, right? But if you average them out, the expected value is zero. Okay, when you deal with probabilities, this is very commonplace, right? Uh, Always we do that. Um, it's just samples taken over a period of time, right? And calculating average, sometimes positive, sometimes negative, and all that. But if you add them together over a period of time, and expected value is zero, right? This is a major uh, uh, constraint we put forward right at the beginning of developing Kalman filter. We want the Kalman filter to be something like this. Okay, where expected value of the error is zero. And also we want another thing, that is the covariance, right, between estimate and the true variable, actual value, true value, which is unknowable, right? Not only the mean is zero, but it should not vary too much. If you say you have a predictor or estimator which predicts a value with a huge error, and it's random, sometimes negative, sometimes positive, but huge amount, it flips back and forth, right? But when you average it out, it's zero. So you can satisfy this first condition, even with a higher variance. It flips back and forth, but average is zero. That is why we put the second condition also in place, right? It should not vary too much. So it should be very small variance around the mean value. Okay. So minimize the variance. So these two uh, constraints or properties are very significant in developing the Kalman filter. All right. So with these two assumptions or other constraints, when you design something, you can put the constraints up front and then design the system so that these constraints are not violated. Okay. So the filter design is based on these conditions, right? Uh, Zero bias, which means expected error is zero, all right? Unbiased estimate. And also minimum uh, variance in your estimate, which means your estimate should not be predicting values randomly too far away from the actual value. So you estimate now and after 1 minute, after the next instant, and so on, right? Series of estimates should be closely distributed around the actual state, right? Okay. Now again, there are some preliminaries you need to know. The in linear algebra, right? Because in the filter derivation, these theories are used. So the first one I want to show to you is that we know the state is a vector, right? Column vector. And if you have a scalar out of the states, right? Like what we had earlier, Z. Um, so Z is a scalar function of the states. You can get the states and combine them together in various ways and produce this scalar. Okay. So now, if you differentiate this scalar, which is a function of the states, right, with respect to the state vector itself, okay, this is how we define. So you get the scalar and differentiate with respect to the first state variable, and then you take z and differentiate it with respect to the second state variable x2, the third one up to whatever number of states you are having in the system, right? Partial z over partial xn, the last state variable. So this is how we define the partial differentiation of a scalar with respect to a vector, with respect to a vector. So eventually the result is same dimension of the state, okay, state vector. And similarly, if you think of a matrix, say for example A, the matrix is elements of the matrix um, are generated by the state vectors, right? The state variables rather. So maybe something like this. So uh, if you look at the differentiation of the scalar with respect to the matrix now, earlier is with respect to a state vector. Now it is with respect to a matrix. You are differentiating a scalar with respect to a vector and now with respect to a matrix. Okay. And the result here is something of the same dimension as of the matrix. Similar to the earlier case, when you differentiate the scalar with respect to a vector, the result is the same dimension of that vector. Okay. So it is the partial derivative of the scalar with respect to the first element, a11, and then a12 with respect to a1n. Okay, that is the first row, second row, third row, and so on. So remember that, okay? You can actually differentiate a scalar with respect to a vector or with respect to a matrix, and this is the result, right? If you don't know, I'm just recalling your memory. What about this one? If you have two vectors, x and y, right? They are both column vectors. And you transpose one of these vectors so that it becomes a row vector. And then you multiply with the column vector, same dimension, okay? So it is element-wise multiplication. The first element in x gets multiplied with the first element in y. Second element in x gets multiplied with the second element in y, and you add them together, and you keep going, multiply, add, and so on. So that is x transpose y operation, right? Uh, and then you differentiate it with respect to x is a column vector, right? And result is y. Result is y. And if you do it the other way around, get y first and transpose it, and it becomes a row vector. and then multiply by the column vector. Again, like element-wise multiplication, you will end up having the same scalar. And now differentiate with respect to x. Okay, you end up having same y. All right. So you can understand this without any proof, I'm sure. But if you want to have a proof, here it is. So we get x as x1 up to xn. And we have the second column y from y1 to yn, rather, it should be yn over here. Okay. And then you multiply them together, x transpose y. Okay, this is a scalar eventually. This is the element-wise multiplication I explained earlier. So the result is x1 y1 plus x2 y2 up to xn yn. They are all scalars. Add them together. So it's not a vector or a matrix, right? It's just a scalar. Now this expression, right? We gonna differentiate with respect to x1. So if you look at this one with respect to x column vector, first you differentiate with respect to the first element of the vector, that is x1. The result is y1. Then you differentiate this with respect to the second element, right, of the differentiating vector, that is x2. The answer is y2. And you keep going like that until you differentiate the scalar with respect to the last element of x. The answer is, look at all these things, only this one depends on yn. So xn, when you differentiate with respect to xn, the answer is yn. All the other things in the differentiation is 0. So when you then line up all these partial derivatives as a column, the result is y1 up to yn, which is y. So this one. Okay, so this is just the proof of what I just mentioned over here. Another one, if you have an expression like this, x transpose nx, all right, n is a symmetric matrix, x is a vector, all right, and you differentiate this with respect to x. X is a column, right? Again, you have to differentiate with respect to each and every variable in x vector. The result is 2nx. Again, we'll demonstrate that with this x column vector, x1 to xn, and n being n by n symmetric matrix. Okay, by the way, this is not only, this is not a diagonal, it's a symmetric matrix rather. Okay. So you know what a symmetric matrix is. Now, if you look at the off diagonal, right, elements are mirrored from one another. So they're not different to each other, right? If you have, say, at the top right corner some number, you get the bottom left corner the same, right? The diagonal is kind of mirrored. So you see the symmetry, right? The corresponding elements on around the diagonal on either side are equal. So example, we have two state vector x1, x2. Let's say n equals a, b, b, c. This is symmetry, main diagonal AC, and the two elements either side, so they are equal. Now, let's first get the scale, this expression workout, x transpose nx, right? X transpose is a row vector, n is the symmetric matrix given, and then x is a column vector. So when you multiply the first multiplication, x1a plus x2b, second element x1b plus x2c, like this one. Then you multiply it with x1, x2, this is the result. Okay. So when you simplify it, you will see it is ax1 square plus 2b x1, x2 plus c x2 square, right? So now what we want to do is we want to show that this is same as 2nx. So when you differentiate this, sorry, this X transpose Nx is only this scalar, then you have to differentiate with respect to the column X, so which has two elements, X1 and X2. So you have to first differentiate this with respect to X1 and X2, and then show that it is equal to 2nx. So first we differentiate with respect to X1, and the answer is 2ax1 plus 2bx2. So this is coming from this expression. Differentiate with respect to x1. So 2ax1 is a result plus 2bx2 plus 0 is independent of x1. And you get the expression differentiate with respect to x2. This is the result you get, right? Again, go back to this one. Differentiate with respect to x2. This is 0. This is 2bx1. This is 2cx2. Okay, right. So when you combine these two together, this is the result, right? And now if you put 2 times, this is n, this is x, you get the same result. Look at that. A times x1 plus b times x2, right? Ax1, bx2. And then the second column, bx1 plus cx2, right? And this 2 is required to match it with the left-hand side. So 2nx. So it's a nice experience for you to do it yourself. Please do that, all these things later at home, right? All these differentiations and identities. Please spend some time, about half an hour, 1 hour, and go through all of these things so that it will go to your brains, okay? Because the Kalman filter is a statistical filter, as I said earlier also, you need to have a proper understanding about signals, random signals, distributions, what we call mean of a signal, standard deviation, variance, covariance, things like that. So I don't assume that you have a proper understanding about all these things, but I don't want to spend a lot of time on that either. So therefore, I have just one slide to talk about variance, mean, etc. Okay, going through an example. This will help you refresh your past memory about probability and statistics, right? Uh, let me first take two signals, X and Y, right? Two signals. If you look at signal X, the value is 2, 3, 1, 4, 2, 1, 8, 6, 7, like that. So every second you read a sensor, something like that. Maybe it's a sensor reading. And there's another sensor here, Y. It gives you 5, 4, 2, 1, 3, 1, 8, 4, like that, right? So this is what we see, right, coming out of the two sensors. Now we have to process the signal and figure out or extract additional information, all right? First thing we do is that multiply uh, the values given by the two sensors at each time step, right? That is x, y basically. So 2 times 5 is 10, 4 times 3 is 12, 1 times 2 is 2, like that, okay? So this is the product. Now, let me start with something everybody knows about, that is mean of x. Mean of x is sum divided by number of readings, okay? Number of samples. So summation of x divided by n. The answer is 34 over 9 because you have 1, 2, 3, 4, 5, 6, 7, 8, 9 samples. When you add them together, check that out. I got it 34, right? I just wrote these numbers randomly without having any pattern in it, right? Um, the answer is 3.78. This is the mean of this signal, mean of this signal. But as you can see, not even one of the samples is exactly equal to 3.78. There is one very close to it, that is number 4, very close to the mean, 3.78, right? Then the next one is 3, right? Most of the samples are far away from the mean. So the samples vary, right? Therefore, the mean is actually, I don't say meaningless. It has a little meaning because none of these samples are close to the mean, 3.78, right? So when you deal with signals, what matters to us is what we see at that moment of time. What we see at that moment of time, because we are going to react to that. So if the average is 3.78, but at the moment we see 8 or 6 or 7 over here, we are actually getting not very correct information. And if we act on that, we are not doing the right thing. So that is why this variance is also important. Okay. Mean doesn't really mean anything if the variance is too much. Look at the second signal, y, and calculate y bar. Y bar means mean. Okay. Summation of y divided by n is 9 as in the x case. Now the total is 29, 3.22. So the average of this signal is 3.22. Okay. All right. So now let's move on to the right hand side here. Now, if I ask you what is the variance of x, this is when things become a bit more confusing, right? What is the variance of x? I already mentioned variance is how much the individual samples, instantaneous samples, like flip around, right? You never get the mean, or very rarely you hit right at the mean, but most of these samples that you get are either on the left hand side or the right hand side, or up or down, right? So now we want to get a measure of this variation, right? Maybe it's a little variation around the mean, or maybe wider variation. So we want to get to that. That is why variance is defined. So how do you define the variance? If you think of just one signal, let's say x, okay, you can work it out like that. You get the squares of instantaneous samples, add them together, divide by number of samples. So this is again another average, but it is the square sum, right? It's like root square mean. So no root, square mean. Okay, square mean. So get the squares and divide by number of samples. Square mean minus mean square. So this x bar is the mean and square. Before that, square mean. So all of the instantaneous samples get the squares, then you, even if you have negative values, they become like positive in square terms. Minus mean square. Then you have some idea about the variance rather. Okay. So for x, the first state variable, the the answer is, if you get the squares, say 2 square plus 3 square plus 1 square plus 4 square, like that, it's 184 divided by 9 minus mean is 3.78. Get the square of that and deduct. Answer is 6.16. So this number tells you something about this variation, right? Around which area, narrow or wider area, the samples are distributed around the mean. And if you do the same thing for y, you can see the covariance here, y. And this is covariance of x. Covariance, right? Same signal, xx. Here, yy, right? And square average, square mean of y is, get the squares, 5 square plus 4 square, 2 square, like that. I think it's total 137 over 9 minus mean square, 3.22 square. Answer is 4.85. Immediately you can see the two signals, X and Y. X has a larger covariance or wider covariance, somewhat, and compared to Y, the covariance of Y. So covariance of Y is 4.85, covariance of X is 6.16. So this tells you that in case of Y, the samples are random, right? You never hit the average, but either on the left or right hand side, but it appears more often around this margin. Whereas if you look at X, it goes a little farther, right? A little farther. So if I have a choice to use one of these sensors in my measurement, I would definitely go for sensor Y, not sensor X, right? Because its variance is smaller or narrower than in X. Now this word covariance comes because you have two signals. But of course here, either case, it's just one signal, but we have taken it twice, X and X, here Y and Y. But actual covariance comes when the two signals are different, X and Y, like in the middle case over here. Okay. Otherwise, the covariance means the same signal taken twice in the square, same signal multiplied with the same signal at each instance. Okay. But this one in the middle is different because you are combining X and Y together, right? Look at the definition. Uh, Covariance of X and Y. This is how you do that. It's not the square mean now. It's the product of X and Y element at each step, and then you add them together. It is the uh, sum of products average, okay, between X and Y. So 2 times 5 plus 3 times 4 plus 1 times 2, like that. The total is something and minus the two means, the product of the two means. You can see on the left-hand side, this is instantaneous products. And here, the product of the two means, X bar, Y bar. The answer is 2.5 here. Okay. Now, what does this mean? The covariance of Y, Y and covariance of X, X, we have some idea. Okay. It's about the variation, the positioning of the values, right? Readings around the mean. This one tells you something else. This one tells you how X and Y are related to each other or not related to each other. Okay, because these two signals, right? Maybe they are coming from some same source so that they are related to each other. Or maybe they are coming from totally independent sources. So therefore, they are not related to each other at all, right? So in control systems, we have noise and other signals, disturbances. They're sometimes related. They're coming from the same source. So we want to find out whether these two signals are related to each other. So for that, we have what is called the correlation coefficient calculator. This is the correlation coefficient. Gamma, or sometimes we give another symbol, is equal to covariance, this one, of the two signals divided by the square root of covariance of individual signals. If you look at X, there's some variance, right, of X. And if you look at Y, there is a variance. We call it covariance rather. When it comes to the same signal, we don't sometimes use this covariance thing, right? We just say variance. But I think if you want to use variance and covariance, you are confusing yourself. So it is better to stick to the word covariance. It's generally applicable whether you are having two signals or one signal. But if it is just one signal and you want to find out the covariance of one signal, we don't use this co thing. We just say variance. Okay, right. So that is why up here I have written either covariance of xx or variance of sx. They are same meaning. Now back to the correlation coefficient. If you want to check whether these two signals are coming from the same source, something sharing between these two signals, you want to calculate the correlation coefficient. And this is the definition. Get the covariance, right, between x and y. I think we have got it 2.5 early. Divide by the product, the root of the products of the two variances, right, independently. X, you have this variance, y, you have this variance. We have got them also 6.16 and 4.85. The answer is 0.46. Now, how do we interpret this 0.46? That is the biggest thing, right? Now, let me tell you, because this is not a statistical lecture, right? But I can just tell you this. When you calculate the correlation coefficient between two signals, right? Always it's between two signals, x and y. The number that you get, right, could lie between -1 and +1. -1 and +1, okay? So if the two signals are related to each other strongly, the answer is 1, right? If the two signals are not correlated at all, the answer is 0. If the two signals are totally random signals and they are not related to each other in any way, then the correlation coefficient is 0. If the two signals are related in the opposite direction, which means when one goes up, the other goes down, right? It's also a relationship, but negative. So the correlation coefficient would be -1 in that case. So it could be -1 to +1. Right? Depending on the strength of this correlation, you get the number. Now here, the answer is 0.46, closer to 0.5, right? So we can see the two signals x and y are sharing something in common. They are related to each other, which means when x increases, y also increases. That this tendency is there. If you look at that one, you can see 2 becomes 3, then 5 becomes 4. That that's exactly opposite, right? But the next one, then 3 becomes 1, 4 becomes 2. Oh, there you are. This reduces and this also reduces. Then 1 becomes 4, 2 becomes 1. That is the opposite again. And then 4 goes to 2, 1 goes to 3. That is also kind of opposite. 2 to 1, 3 to 1. That is correct. 1 to 8, 1 to 8. That is correct. Right? 8 to 6, 8 to 1. That is also correct. 6 to 7, 1 to 4. That is also correct. So because when the signal increases, the other one is also increasing. So, but it is not a very strong thing because you saw some opposite trend also. When 2 goes to 3 in X, 5 goes to 4 in Y. That is the opposite trend. So therefore, you don't get +1 here. You don't get +1 here. So if you have, say, sinusoidal goes like that, and another sinusoidal goes with the same frequency with a small amplitude, that's a perfect correlation between the two. Then your answer would be 1. But here, there is some sort of trend. When x increases, y also increases, but sometimes there is the opposite way, right? X increases, y decreases. So therefore, the correlation coefficient is 0.46, like only halfway. All right, is everything clear up to now? With that, we can actually formally start the presentation and discussion on Kalman filter, right? First, we assume a linear system, right? So that you can model the plant using the state space model. Xk plus 1 is equal to phi k plus 1 xk plus some omega k, right? When I write that you see something similar, right? You have seen before, and also it's bit different, right? So the first part over here is the state transition, right? We have done this before. Xk is the state at step k, and xk plus 1 is the next step, right? The transition. So even without any additional controls, the system changes itself, and it is defined by this capital Phi. Okay. Uh, this part here is the unmodeled dynamics. Now in Kalman filter discussion, we use the unmodeled dynamics. All right. So before that, in most of our discussions, we did not use unmodeled dynamics, and we assume system is um, accurately modeled. Or if there's any unmodeled dynamics, right, it will create a response which is not what we expect, maybe with a little error. And when you feed it back, there's an error. So the controller is there to recover from that error. Okay, so somebody is actually controlling the system so that you can accommodate, you can accept unmodeled dynamics in the plant, right? You don't have to have perfect model, right? In fact, no model is perfect. Always there is something unmodeled, and because of that, there's an error always. So that is why we need to have a feedback loop, right? To figure out, even though we did the right thing, the best thing possible, still there's an error because of unmodeled dynamics. The controller will look at, okay, don't worry about what happened, so I can fix the problem, right? So that is what the controller does. Now, in this discussion, we use that one, unmodeled dynamics. Now, the thing is, because it is unmodeled, nobody knows it. It's just a symbol over here. In case of Kalman filter, we assume omega k to be a random noise, right? With zero mean Gaussian noise. So there's zero mean thing, it flips back and forth, back and forth. Some sort of noise coming from the system, some random noise. Now, this is arguable. You might ask, how can we have that kind of thing? Well, if it is a systematic thing that we did not model, of course, it won't be zero mean Gaussian distributed noise, right? If you have missed to model a certain physical item in the plant, right? Then you are missing something, something more meaningful, right, in the plant. So we are not referring to something like that here. After modeling all these things, there's still some sort of random noise in the plant. Okay. So that is this WK or omega K. We have another equation we call measurement equation. This is basically the sensor, right? So we give the symbol Z for that, ZK. The measurement at kth instant is equal to HKXK. You have seen this before, right? Some of the state variables um, are read, right, using HK. You may have n number of states, but your reading is just one of them, or maybe combination of first two, something like that. Or maybe the last one, right? Depending on the configuration of your vector. And the sensor has its own noise, and that is VK, sensor noise, right? So our two equations are A and B. So this is how this is a model we discuss, we use in Kalman filter derivation. So I can show you some, say, an example, a second order system, x1, k plus 1, x2, k plus 1. So that is basically this equation, right? xk plus 1. Sorry, the left-hand side of the first equation, which is equal to 1, 2, minus 1, 1. This is the state transition matrix. This is xk, x1k, x2k, plus this is w1k, w2k. So state variable x1, right, has a random noise, random fluctuation around its mean value. So is x2 state variable, right? It has some value, but it changes. It varies around that mean value. Now, the equation number two, or B, equation B, Zk, if you have two sensors, right? You can say Z1 and Z2. You're measuring position and also velocity. It is a vehicle, right? So in that case, H would be something like this, 1001, right? So you measure X1, you measure X2. First, rho says that Z1 is equal to X1 plus omega 1K. So it measures X1, okay, plus a little noise is added. That is the sensor reading. Second sensor reading is equal to X2 plus V2K. So it has its own noise addition. V1 and V2 are not the same. So is W1 and W2. So you can write down these four equations, two state equations and two measurement equations. And both of these sets, the equations, right, has this noise, randomly distributed noise, zero mean, and with some variance, okay? So W has its own variance and V1, V2, they have their own variances, right? So this is basically the model we are using in Kalman filter derivation. Again, I'm showing you here the same diagram I explained to you earlier. So we have the plant to which we give the control signal. The plant has A and B matrices, and it produces Y, right? In fact, this Y is measured by the sensor and it produces Z. Now you can see this Z, right? So look at that difference. Y is the actual uh, state as a result of the control signal, right? Actual response. But it is measured with a sensor and sensor produces Z, right? Now, there's a difference between Z and Y because sensor noise, right? You can see it over here. This Y could be X1 or X2, right? Or Y1 and Y2, right? Over here, Y1 is measured and the result is Z1. Y2 is also measured using a sensor and the sensor gives you Z2, right? Like that. All right. Any questions? Now, this is a very generic system where you have two readings. Okay. So, and for each reading, there is a sensor output, right? For simplicity, you can just have one reading, one output. Okay. Okay, so some preliminaries about the Kalman filter. Uh, we assume the unmodeled dynamics of the plant, right, has zero mean noise, zero mean unmodeled dynamics, right? So expected value of W, W1 or W2, whatever it is, for a fairly long period of time, the answer is zero, okay? And so is the sensor. If you look at sensor data sheet, it might tell you, okay, what is your mean error? Probably it is zero, but there's a variance. And we also assume that the unmodeled dynamics, whatever um, response change or state change because of unmodeled dynamics, has nothing to do with the sensor noise. Of course, it is visibly true, right? We don't expect any relationship between the sensor's noise and the system's unmodeled dynamics. So sensors noise, systems noise, right? They are more often than not uncorrelated. So therefore, the covariance between the two is zero. Okay, we assume that. And if you look at the process noise, the unmodeled dynamics, and because of that, the change in the state variables, right? So you know that it randomly fluctuate. So there's some variance there, and we give it a symbol Q, right? This is the process noise covariance. Now, when I say covariance, you know what I mean, right? Because we looked at an example also. We know what the covariance is, how much it varies, right, around the mean. And if you look at the sensor, sensor has its own variance, sensor noise variance. Okay, so we can say it covariance or variance, but I think covariance is better because it's not just one signal now, right? It's not just one signal. There are so many. If you look at state variables, if you have 5 states, right, you are talking about 5 variances, right? X1, X2, X3, sorry, W1, W2, W3, and so on. So these are individual uh, uh, perturbations. Now, when you want to calculate covariance, you get WW, W1, W1, and then W1, W2, then W1, W3. So likewise, it's a matrix of covariance. So we call it covariance matrix. Okay. If it is just one state, it's just a scalar, W1, W1. Even you don't have to say one if it is just one uh, signal. If it is a two signals, right, X1, X2, when you do the covariance, you get W1, 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 W2, W2, W1, and W2, W2. So there are 4 values there. So it's a 2 by 2 matrix. So therefore, we say covariance matrix. Okay. Same as here, sensor noise covariance, right? If it is single measurement that you are taking, you don't have to say matrix or whatever, it's just number, right? Just R. But if you measure more than one readings and you are going to estimate same number of states, right? Then you get this covariance matrix, right? So we assume both the unmodeled dynamics, and because of that, any system change has zero mean, right? Zero mean. So there's no bias. It's zero mean, unbiased estimate. But there's a variance. And in most cases, you need to have these variances, right? Measured and known. And you have to feed it to the Kalman filter. Then only Kalman filter can combine the the plant estimate and also sensor reading together, right, to reduce the errors. Right. So in this slide, this is a very heavy slide, um, which contains the entire Kalman filter, right? If you want to use a Kalman filter in your project, right, you need to have these 5 equations written. Maybe it is in MATLAB or some other language. You have to write it. Or you can use the available libraries. For example, in MATLAB, right, you can use the Kalman filter as a predefined written function which is available for you to use. So you use the function with the required arguments and you get the estimate, right, as an output without actually having to write down all these things um, your own way, right? And if you go to Simulink, there's a Simulink block, Kalman filter. And you get the block, something like that, right? You can feed the signals in and it produces the outcome. In fact, this is what I do most of the time. Don't write the Kalman filter equations from scratch, okay? Right. The first equation I want to show you here is state extrapolation. I will go by the names of the equations. Number two, covariance extrapolation. Number three, Kalman gain computation. Number four, state update. Number five, covariance update. And after that, you roll over from number one again, right? 1, 2, 3, 4, 5, then 1, 2, 3, 4, 5, then 1, 2, 3, 4, 5. It's a recursive algorithm, right? Every instance, you have to run these 5 equations. Of the 5 equations, the first two we call the predictor. The first two equations, we predict something, right? It's not very true, but we make a prediction. And the last two equations, we correct it. We predicted something, right? And now we correct it. Why? When you do the prediction, you don't have the sensor feedback. For example, you drive your vehicle. You don't have GPS, right? Say you have GPS, but it has not come yet. Okay. Even if you have the GPS, you keep it aside, right? Either case, you look at the wheel, how many turns, right? Uh, from the last stop, and then you calculate the distance, and that is the predictor. Then you predict, okay, this must be my position. So this is done by these two equations. Okay. Now after that, you get the GPS data and correct the error. Now you know that you have to predict it is not very accurate. You have to correct it using the GPS data. Okay. This process is called the correction. Now in between, there is a very interesting step, Kalman gain computation. For you to implement the correction, that is combination of the state prediction plus the absolute measurement, GPS or whatever, you need to have a Kalman filter gain, right? This gain, how much of this versus how much of that, how do you combine it, right? It is taking bit of prediction, bit of correction and put them together. Just like that. Uh, say if you're pretty sure about your own measurement, right? You are more faithful to that measurement. Okay, you take your own measurement very seriously, right? In that case, you take 80% of that into your estimate and 20% of what the GPS says, right? Maybe in a very gloomy condition, you don't have enough GPS satellites and you get a prediction and you know that this is not going to be very accurate, right? But you can take a little of that, maybe 20% from that and 80% from your own measurement, looking at the wheel of the vehicle, okay? So because it's also pretty accurate, right? If there's no wheel slipping, you can count the number of turns, right? And multiply by the circumference and you know where you are, okay? So that is the prediction and correction comes with the sensor reading, okay? So as I said, the prediction doesn't take place because there's no sensor reading. Even though you have the sensor reading, this is how the filter works. It first calculates the prediction using the system model, okay? And then you use the sensor feedback and correct your estimate, okay? So it's a predictor corrector architecture. And in between, you have the Kalman gain computation, right? You calculate the gain, which tells you how much of GPS versus how much of the wheels, okay? This combination. So in the derivation, we have to derive all these 5, right? Um, but to illustrate to you what's happening in the Kalman filter, it's like this. The first two equations is the predictor, as I already mentioned, and then we compute the Kalman gain, and then you go to the other two equations, 4 and 5, corrector, and then you feed it back. It goes on and on and on. So let's look at the first step, equation number one. Okay. Let me show you how we arrive at this, how Kalman actually derived this first place, right? If you look at this statement here, state prediction using the model without considering unmodeled dynamics. So there's some unmodeled dynamics, right? This W term is the unmodeled dynamics. This term. Initially, we don't consider that and write the equation like this. So this equation is not identical to what you have seen earlier, right? In the system model, this one. This is how we write the system model. But now when you use it in the Kalman filter, because it's going in 4 equations, right? At each step, right, the state is different. So when you use this equation in the Kalman filter, first you don't take this WK, okay? So it is just this. And also in place of X, I now write X hat because it is the Kalman filter estimate. In this model, it is the true state, xk plus 1. Right? Even though we don't know the true state, this is the plant model, right, that we use. And we rely on this ZK, the sensor measurement for feedback and control. Now in Kalman filter case, we write X as X hat when it comes from the Kalman filter. We write X as it is when we refer to the actual variable, right? So you can have xk measured by or predicted by Kalman filter. Then we put the hat on top of that. Now you understand what this equation means, right? X hat k means Kalman filter estimate at step k, right? So this is the Kalman filter, right? It predicts something at step k, and that is xk. You can see it over here. This hat comes when the variable is coming from the Kalman field. And this is the state transition matrix. And this is xk plus 1. So next moment, the prediction would be like this. If you know your xk, x hat k, you can calculate your x hat k plus 1, right? If you use this particular model, we write this as negative, which means just a prediction. Process is not done yet. This is just the beginning of the Kalman filter. Initial step, we predict state to change from xk to xk plus 1 hat with a negative sign. So negative sign indicates that we are in the first step, predictor stage. Okay. The negative symbol here indicates it's a predictor, still in the predictor, right? This is kind of foundation. We have to build the process on top of this, right? Now we say this after going through this process, right, Kalman filter, eventually you get x hat k plus 1 without this minus sign. Because once you go through the corrector phase, you don't have negative sign. So negative is there to indicate that you are still in the predictor state, right? When you calculate the Kalman gain, like over here, and do the Kalman gain and do the predictor, right? It is x hat k plus 1, not x hat k plus 1 minus. This is predictor, this is corrector, okay? Right. So this corrected value, this is the final estimate of the Kalman filter, x hat k plus 1. If you deduct xk plus 1, there you are. This xk plus 1 is the true state of the plant. oops, here, this y, right, comes from the state x. It is the true state of the plant, x. And here you have x hat, what the Kalman says. You get the difference between the two, and that is the error, right? There you are. And if you have an error right now, and there's another error next moment, and so on, take some time, duration, and get the average expected error. It should be 0. All right. We tell to the Kalman filter that we want a filter like this. Now, the fusion of the two signals. One is the model predicted value. You can see it over here, right? What the model predicted, right? Um, x hat k or k minus 1, right? That is what the model predicted, right? Model predicts rather. Uh, and there is a sensor which tells you about the reading, right? So when you want to combine these two together, this is the equation we are using, right? In the Kalman filter. What is that? This x hat k plus 1, right? Uh, the filter estimate, this one, x hat, right? K plus 1 uh, is actually generated using x hat, and zk plus 1. What is zk plus 1? That is the observation coming from the sensor, right? Sensor tells you something, sensor reading. And also Kalman filter has predicted some value in the previous step, okay? Previous step. So filter combines these two together. This is what the Kalman filter uh, 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 estimate the previous time step, right? And you multiply it with uh, k dash k plus 1, and then you get the observation, that is zk plus 1, and multiply with k plus 1, right? So if the previous estimate, right, x hat k is more accurate, then you can have higher value for k dash k plus 1 to take more from that, right? And if the observation is very clear, accurate, you have a good sensor, you can have this k to have a higher value. So which means you're taking more from the observation, less from the state prediction, or vice versa, right? Depending on which one of these two is more accurate. So it combines the previous estimate and the current estimate. Oops. All right. Okay. Now, let's write the first constraint, right? What is that? Uh, we want the expected error to be 0. Right? This is one of the constraints of the Kalman filter design. The estimate needs to have 0 mean. So when you define the error, it is estimate minus actual, right? And the mean error should be 0. Over a period of time, you get the errors, add them together, divide by number of samples, answer should be 0. This is how we write in statistically, right? Expected value of the uh, filter prediction minus actual. Filter prediction minus actual. Now, if you take this equation and replace x hat k plus 1, x hat k plus 1, you can write it down like this. This is x hat k plus 1 coming from equation C over here. Kalman filter predicts the estimate. Oh, sorry, correct the estimate. Right? It gives you out this estimate using this equation. It combines two things together. State, estimate, previous time step, observation now. Using two weights, you add them together. It's like weighted average of the two signals, right? So what you do is you take this right hand side of the equation C and put it over here to equation 6. So this x hat k plus 1 is substituted by this expression, right? Two terms. Then you can write it down like this. This is the actual state. Okay, so this equation says expected value of the error between or difference between the Kalman filter estimate and the actual value, right, is 0. Now what we do is we change um, from equation B above. What is that? I will show you that equation. I think no need to go back because you can understand that right over here, right? So this is actually Z, right? The measurement. Output equation, Z is equal to H times xk plus 1 plus V. V is the sensor noise, right? In fact, if you want, I can go back to that equation way back, I think. Oops, where is it? This one, this equation, right? Output, sorry, the sensor measurement is equal to H times X plus V. So we replace this Z, sensor measurement, at k times 1, k plus 1 instance. So hk plus 1, xk plus 1 plus vk plus 1. So here is a true state, actual state, measured by the sensor. And in front of that, you have k plus 1, some constant. And the first term remain unchanged minus xk plus 1, right? Actual state. So this is again the error. First part up to this point, this whole thing is the Kalman filter estimate at k plus 1 minus actual state. So this is the error. Now what we do is we add and subtract the same term over here, k dash k plus 1 xk. You add that and you deduct that. So it's all right, right? But when you do that, you can take these two terms in separate places and write down this equation. It's a lengthy equation, but I can walk you through the equation. If you look at k dash k plus 1, it's over here. And then you have x hat k, x hat k. And you take this one, this new term, which is added and subtracted. You take this one over here and put minus xk, right? Minus xk. And take k dash k plus 1 as a common factor. The moment you do that, this is another error, you know, x hat k minus xk. This is Kalman filter prediction, Kalman filter estimate rather at step k minus the actual value at step 2. So this is the error in the previous step. Okay, error between the Kalman and the plant. Okay. Then the second term k plus 1, you keep it as it is, and then hk plus 1, xk plus 1. So x is the state at k plus 1, and you can write it down as a state transition from xk. So xk times phi k plus 1 plus the plant noise wk plus 1. Okay. So you substitute that from equation A, go back, equation A is there, plus Vk plus 1, sensor noise, minus, again you have Xk plus 1, you replace it with the system dynamics, state transition rather, uh, and then plus K dash K plus 1 Xk, this term is over here. The next step, you keep the front part unchanged, right? But what you do is you expand this equation here, the bracket rather here, hk plus 1, phi k plus 1 xk as one term, and then you take this term, phi k plus 1 xk term into over here, right? And also the last term over here, k dash k plus 1 xk, because these are xk terms, right? You have here xk term, you have here xk term, and here also xk term. So you combine these three terms together here and write down xk out of the bracket. So three terms in here. And then you have wk plus 1, right? Times hk plus 1, right? Times k plus 1, right? So you write it down over here. And also you have another wk plus 1 over here. So you put I here to represent it in the bracket, and out of that wk plus 1. Then there's another term, the final term missing is k plus 1 times b k plus 1. So which is this one multiplied with this k plus 1. This term you write it over here. Later, take your time and go through this process and identify the terms, where they go, where they combine and all. These arrows will help you navigate through the process. Now, finally, what you have is the expected value of these long expressions. Okay, so we started off with a simple expected value, that is Kalman minus plant error between the two. And now it has been expanded into a long expression. So when you have a expected value of a long expression, you can take the expected value to individual and then add them together, right? So this is what we do at the end. So I take the expected value of the first term here, that is k dash k plus 1 is a constant, times the expected value of x hat minus xk. That is the first term. Then you have this entire expression times expected value of xk. There you are, expected value of xk, right? That is the second term. Third term, k plus 1, hk plus 1 minus I, expected value of wk plus 1, right? Last term, k plus 1, then expected value of pk plus 1. We have four terms. We get the four expected values, add them together, and answer should be 0. In that case, you have a zero bias or unbiased estimate, which means your estimate and the plant state will be very closely apart, right? Mean is actually 0. Now, interestingly, out of these four terms, last two are 0 anyway, because these are, we assume W, that is uh, the process uncertainty, right? Process uncertainty, because there's some unmodeled dynamics, so that there's a noise. The state variables change, right, with zero mean, but with a variance. But because we assume zero mean, because we can't take them any further, right? The expected value is zero. So is the expected value of the sensor. Sensor doesn't have any bias. It's zero mean, but there's a noise, right? Fluctuation, but mean is zero. So these two things anyway are zero. Then you have the first two terms. Now, if you look at these first two terms, right? First term, x hat k minus xk. This is the error last time, a step back, right? And when you go this recursive equation, right, you have the error in the previous step, you have the error in this step, right? So the whole thing comes with the step, the error at k plus 1 step coming from k, right? So if we have this kind of filter with zero bias, zero mean error in the previous state, then this is zero. In that case, this is zero anyway, because this is x hat k, that is Kalman, minus xk, that is actual plan. The expected value is anyway zero. So if it is zero in the previous step, and we want it to be zero now also, that is why, that is the constraint, right, in filter development. So therefore, we say that whatever comes in front of this, within this matrix, bracket, should be zero, because exk is not zero. Expected value of xk, is it zero? No, it is a state variable. State variable has some value. What goes to zero is the error between Kalman and the plant. So therefore, this is anyway zero. This has to be zero, right, for this condition to be met. So what is this bracket? It's a long chain here, k plus 1. Rather than saying k plus 1, I would say kh phi minus phi plus k dash. K dash is the weight given to the measurement. K is the weight given to the plant model, right? So this bracket, whole thing should be equal to 0, right? So this is that condition. From that, you can say k dash k plus 1, k dash k plus 1 should be equal to 1 minus k plus 1, hk plus 1 times state transition matrix k plus 1. So this is a very interesting equation for zero mean estimate, right? Uh, k dash and k should be related in this way, right? Can you see that? So when k is bigger, this is smaller, and vice versa. When k is smaller, k dash is bigger. This is exactly what we expected, right? When you have a very good sensor, k is big. In that case, k dash is small. Then you don't have to rely on this measuring the turns of the wheel and all that, right? If you have a pretty good GPS, like differential GPS or RTK GPS, which gives you few centimeter accuracy, don't worry about measuring the wheel turns, right? And on the other hand, if you don't have proper GPS, right, you're not very sure about your commercial grade GPS, which is working at maybe 5 hertz or 2 hertz, and error is about a couple of meters, right, 4 to 5 meters, then your sensor measurement is not very reliable. In that case, your k is small. Then you start measuring the wheel turns and calculate where you are, right? So you increase your K dash. Right. So this is very interesting finding. Filter is not completely done, but we have reached a very important step in the process. Right. Any questions up to now?